This will be presented by Mr. Shiroman Prakash. It's my pleasure to welcome Mr. Shiroman Prakash. Mr. Shiroman Prakash is a research scholar at the Department of Theoretical Physics, Tata Institute of Fundamental Research in Mumbai. He obtained his bachelor's degree in physics from Johns Hopkins University in 2005 and received the outstanding minor in computer science from the computer science department. He represented Johns Hopkins in the World Finals of the Association for Computing Machinery Intercollegiate Programming Contest in 2004. He obtained MSc in physics from IIT Kanpur in 2007 and received medals for Best Academic Performance and Best Project Work in the second year. He is presently pursuing PhD in string theory at the Department of Theoretical Physics at TIFR. I welcome Shiroman Prakash.
Thank you very much for inviting me. The talk is on string theory and holography. So the goal of this talk is just to create a qualitative appreciation for the mysteries and richness of quantum physics. And what we'll do is we'll just motivate some recent developments in string theory using general arguments. And of course, we don't know if string theory describes the real world, but we'll see there's many ways in which it might be able to. Outline of the talk, first we'll just mention black holes, then quantum field theory, then quantum gravity and string theory. So the story begins in World War I. So while serving in the German army on the Eastern Front, Karl Schwarzschild discovered the first exact solutions to Einstein's equations of general relativity. So as he wrote, okay, as you can see, the war has treated me kindly enough, in spite of the gunfire, to get away from it all and take this walk in the land of your ideas. So what are Einstein's equations? So Einstein's equations come from Einstein's geometric theory of gravitation. Space and time form a dynamic geometric entity that curves in response to the energy it contains, and Einstein's equations determine the shape of space and time. So the Schwarzschild solution is a spherically symmetric solution of Einstein's equations representing the gravitational field due to a point mass. And although not immediately recognized, it turns out that the Schwarzschild solution has several remarkable properties that remind us that gravity is very different from the other forces. So in particular, the Schwarzschild solution possesses an event horizon. So if you get too close to the center of space-time, you'll cross an event horizon, which is, as you all know, it's just a one-way surface in space-time. So after crossing the event horizon, not even light can escape. And in fact, if you cross the event horizon, you can't send any classical information or causal signal of any kind to the outside universe. Okay, so initially, people thought that the event horizon was unphysical because for an event horizon to exist, the massive object has to be very small, and not even nuclei were that dense. But we now know that such dense objects do exist in the universe, and if a massive object is small enough, the event horizon is real, and it forms what we call a black hole. And okay, black holes exist in nature at the center of almost every galaxy, such as this one, M81, as we see from X-rays and other things. Okay, but for our purposes, what's interesting is black holes and entropy. So recall the second law of thermodynamics: the entropy of the universe must increase. Black holes seem to allow for a violation of this second law, because if you drop an object into a black hole, the entropy of the observable universe apparently decreases. Okay, but Einstein's equations imply event horizons have a special property. In all physical processes, such as dropping matter into a black hole or the merger of two black holes, the surface area of the event horizon can never decrease. In fact, it usually increases. So this led Bekenstein to postulate a generalized second law of thermodynamics. The total entropy of the universe plus the total surface area of all black holes cannot decrease. So in other words, black holes have entropy, and the entropy of a black hole is proportional to the area of its event horizon. So what are the implications for and from quantum mechanics? Okay. So the laws of nature are quantum, and our most precise and accurate descriptions of natural phenomena come from quantum mechanics, but not quantum mechanics of particles, but what's called quantum field theory. And this is just the role, one way of looking at the role of quantum field theory in our description of nature. So let's start with, so Vishal just told us about qubits. So classically, a bit can take a value 0 or 1, but quantum bits can be a superposition of two states. And qubits can also be entangled, and this leads to a variety of strange quantum effects. So how do we go from qubits to quantum fields? So instead of asking, is the bit 0 or 1, we have a system of many interacting quantum particles, and we ask, how many particles do we have in our system, say with a given momentum k? And if it's fermions, the answer can be 0 or 1 or some superposition, and if it's bosons, 0, 1, 2, 3, 4, ... So for fermions, it's sort of like a qubit again, and for bosons, those are the energy levels of a simple harmonic oscillator. But okay, entanglement and superposition again can cause strange quantum effects, so it's not that simple. Now, to define a quantum field theory is difficult, but physically the easiest way to do it is just to use a lattice. So we just start with a lattice, and we put say a qubit at each site. The qubits would interact with their nearest neighbors with a strength g, and we just look at the lattice at wavelengths much larger than lattice spacing, and the effective description for that is what we call a quantum field theory. So non-interacting quantum field theory usually has a particle interpretation, but when there's interactions, the total number of particles need not commute with the Hamiltonian, so it's not conserved. But if interactions are weak, the notion of particles is still an approximately good concept, and we can solve for evolution in a perturbation series in the interaction, in some parameter describing the interaction. So you organize it in using Feynman diagrams, and that can be thought of as two particles colliding, turning into a different particle, then merging again, and each vertex in these comes with the power of g. So since g is small, we only have to keep a few vertices, and we can calculate any physical thing to order g cubed or g to the fourth and still get very accurate answers. But if g is not small, we can't use Feynman diagrams. So how do we calculate physical quantities for quantum field theories? We have to make other approximations, try direct lattice simulations, or in fact, we usually can't say anything at all about strongly interacting quantum field theories. For example, the strong nuclear force at low energies is a strongly interacting quantum field theory, and at least theoretically, it's hard to predict what happens. So, and quantum fields are ubiquitous in nature. In the standard model of particle physics, of course, you have a quote-unquote fundamental quantum field theory describing the electromagnetic force, weak nuclear force, strong nuclear force, etc., and all known elementary particles. But quantum field theories also arise as effective theories in physics, as our construction via lattice suggests. So phonons in a crystal, many interacting electrons in semiconductors, and superconductors are also described by quantum field theories. So now quantum gravity and string theory. So armed with knowledge of quantum field theory, now we can try and make black hole entropy more precise. Where we put the classical black hole into a quantum field. Hawking did that, and we find that the black hole emits radiation at a temperature depending on its mass. So using thermodynamics from the energy and temperature of the black hole, we can again obtain its entropy, and we find the entropy again is proportional to the surface area. So here the entropy equals the area of the black hole divided by 4. And all right, so area here is measured in units of the Planck length squared. So the Planck length is, a dimensional analysis tells us that the fundamental length scale at which we expect quantum gravity effects to become important is determined by these three constants: Newton's constant, Planck's constant of light, and that's the Planck length 10 to the negative 33 centimeters. So now say we want to have a quantum theory of gravity. Just the same way we define quantum field theories of forces, we would try and construct a quantum field theory of gravity using a lattice. So that we could make a lattice with lattice spacing of the Planck length, for example, and each point you might have a qubit. So the question is, can such an attempt work to make a quantum field theory of gravity? Can we use a 3D lattice with qubits at each vertex and make the lattice spacing Planck length and get a quantum theory of gravity out of it? And to answer this question, let's recall the definition of entropy. Again, the entropy of a quantum system is the log of the total number of states the system can be in. So say we had n qubits. There are 2 to the n allowed states. So 0 or 1 for each qubit. So the total entropy is log of 2 to the n, which is proportional to n. So now let's put qubits on a lattice. The total entropy is now proportional to the volume of the lattice because that's how many qubits there are. So in general, for any quantum field theory, we expect the maximum possible entropy or the number of degrees of freedom to be of order the volume of the lattice, right? But now let's consider quantum gravity. So consider a quantum gravity system bounded by a closed surface of area A. How many independent quantum states can it be in? Well, say the system isn't a black hole, but it has some entropy. We could probably add energy, which is the same as mass, to the system and turn it into a black hole. But the entropy can't decrease in this process by the second law. So we expect that the maximum entropy of any physical configuration must be less than that of a black hole, namely area of the surface divided by 4. So a quantum field theory of gravity based on this lattice would have the entropy proportional to its volume, the maximum entropy, but black holes tell us that the maximum entropy has to be proportional to the area, not the volume. Okay, so we realize that a quantum field theory of gravity has far too many microscopic quantum states. Okay, which if you work it out, it comes from the fact that most of the configurations in the Planck-sized lattice have enough energy to form a black hole larger than the volume enclosed. So that's where the overcounting came in. But the point is, okay, if we take black hole entropy seriously, then the observations that 1, black holes have the maximum possible entropy, and 2, that the entropy of a black hole is proportional to the surface area, then that has an important consequence, which is the holographic principle. For gravity, the lattice must be 2-dimensional. Say it could be on the boundary of space-time, or in some way the number of spins have to be proportional to an area, not a volume, for quantum gravity to work. Okay. So this is the holographic principle, and okay, it's due to 't Hooft observed this in 93, and Susskind elaborated on it in 94. So the holographic principle is great, but okay, we have a candidate quantum theory of gravity called string theory, which you may have seen. So this is one way of one picture of string theory. So the question is, how does holography fit in with string theory? And before we do that, what is string theory? So string theory basically replaces point particles by strings. A particle traces a one-dimensional world line string. String trajectory traces a world sheet. A quantum string, we have a quantum field theory living on the world sheet. Okay, so the key definition of string theory, though, is just this, that in quantum field theory, when you have a weakly interacting quantum field theory, instead of you calculate stuff using Feynman diagrams. And in string theory, we calculate the same quantities, but we use Riemann surfaces. So that's at the heart of it, the working definition of string theory. And okay, gravity just comes out of string theory automatically and mysteriously, but the universe must have 10 dimensions and supersymmetry to be consistent. Okay, string theory also contains other objects, which are called d-branes that open strings can end on. So we were asking about holography in string theory, and considering D-branes and the physics of D-branes, Juan Maldacena, an Argentinian physicist, in 1998 found that all the dynamics of string theory in a particular five-dimensional space-time, which is all the dynamics of string theory in a particular five-dimensional space-time is encoded in a 3 + 1 dimensional quantum field theory. So here I'm counting space and time, so 3 space and 1 time dimensions. And 5-dimensional space has 4 space and 1 time. So the space is just a space-time of constant negative curvature. So all the dynamics of gravity, quantum gravity in this 5-dimensional space is in fact encoded in the 4-dimensional quantum field theory on the boundary. And the quantum field theory is not actually a very strange quantum field theory. It's in fact just a highly symmetric version of the theory describing the interactions of quarks and gluons in nuclei. Though the symmetries really simplify the theory, so it is different, but it's not that different, or it's not very strange. And so basically what string theory tells us is that 5D gravity somehow emerges as an effective classical description of the 4D quantum field theory in a particular strongly interacting limit. So this can help understand string theory. It's strong coupling because the string theories are limits of a single unknown quantum theory which has no coupling constant and isn't weakly coupled. So our previous approach defining that doesn't work. So for that purpose, we would consider, so that might help us understand M theory. But more importantly, this observation opens up a new window on quantum field theory at strong coupling, because classical gravity now becomes a good approximation to strongly interacting quantum field theories in a new limit. So the ambitious hope is that, okay, holography may lead to a better understanding of real quantum field theories, such as, QCD in nuclear physics, and recently even systems of strongly interacting electrons in condensed matter physics. And philosophically speaking, we want to create a unified, it may help create a unified theoretical framework for understanding a variety of physical phenomena. So summary. So the observation that black holes have entropy proportional to their surface area indicates that a quantum theory of gravity may be described by a quantum field theory in fewer dimensions, and vice versa. And in fact, string theory provides a concrete realization of the holographic principle called the ADS-CFT correspondence, and people are searching for applications of this correspondence to quantum field theories in traditional areas of physics. So,
what's the current situation with testing of string theory? One reads that there are 10 to the power 500 solutions.
right.
So where does one end up with all that?
Yes, so actually testing string theory as a fundamental theory is difficult, but those 10 to the 500 solutions now have a new interpretation, because those are 10 to the 500 solutions that you can think of that are asymptotically negatively curved. So those are dual to quantum field theories. So that you can think of those as different quantum field theories which you can solve using classical gravity. So now the takeaway is those 10 to the 500 solutions of string theory could describe perhaps different, some of those could describe real physical systems via holography, even if they're not, we don't know whether they're the quantum theory of gravity describing the real world. So.
Yeah, but from the question of falsifiability, if you have so many possible solutions, how do you determine as to whether any of those applies to the real world?
Right. So for string theory as a quantum theory of gravity, that's difficult. I mean, obviously you can find one of. I mean, if there's a way of finding one of these, but the point which I'm trying to make in this talk is the other way around. We can use string theory to model say electrons in a high temperature superconductor ambitiously, or quarks, etc. So then actually these 10 to the 500 solutions, represent 10 to the 500 different quantum field theories that, without gravity, that could exist in laboratories, etc. But for falsification, etc., I mean, we can, that's a more subtle issue. Yeah.
You spoke about tests of string theory in nuclear physics and in condensed matter physics of strongly correlated electrons. The only interface that I know about is this entropy boundaries, 1/4 pi, that comes out of some of these 5-dimensional anti-de Sitter spaces.
Yeah.
Is that what you're referring to? Or,
right, I mean, so that's what we have now, and the ambitious goal is yeah, that's the only, it's not a test of string theory, but a test of string theory as a tool to calculate the strongly coupled behavior of the quantum field theory. Even if these are right, that doesn't mean string theory describes gravity, it just describes. But it's a tool for this.
Okay, well, in that sense, I would agree with you, because I think the only thing that this proves, this entropy bound 1/4 pi, is that you have a quantum field theory, but not necessarily that you have a string theory.
Yes, but it's just a question that here we have some exactly solvable, not exactly solvable but quantum field theories you can study at strong coupling. Yeah, we can extrapolate that to other quantum field theories, that behavior or not.